and what you can prove it. Okay, so that is denoted as the correlation coefficient of x and y. And
Yeah, am I audible?
Yes, sir.
Yes, sir.
Okay. Very good morning. I think screen is also visible, right?
Yes, sir.
Okay. Yeah. So we have covered so far very important discrete random variables, and we started with the Bernoulli. Then we have seen uh, if you do Bernoulli trial n number of time, that will be approximated by binomial distribution, binomial random variable, and so if you keep on repeating the Bernoulli trial for large numbers, then we have another random variable known as Poisson random variable. and which can be seen also as an approximation of a good approximation of binomial random variable. Okay, whenever certain conditions are satisfied. Okay, and then at the end we have defined a random variable, which you are also aware already regarding the geometric random variable. So here the concept of geometric random variable is you are keep on drawing the trial until you get the success. Okay, so this is how this that geometric random variable is generated, and so then the corresponding PMF also can be seen by this. Okay, so at ith number of toss you are getting the success. So and rest I minus one time you are failing. Okay, so 1 minus p is sitting here I minus 1 time. So to the power I minus 1 and into p will be the straightforward probability mass function. Okay, for I equals to 1, 2, 3 and so on, and 0 otherwise. And we have also seen that this satisfies the properties of probability mass function, that non-negativity and normality condition. Okay, right. Now that the following question is there, so I think we can do it within a I think it will not take much time. So you have an urn which contains n white and m black balls. Okay, so you have an urn which contains n white and m black balls. Now balls are randomly selected one at a time until a black one is obtained. So you are selecting balls randomly one at a time, and you are just picking and just okay, and until a black one is obtained. And how this drawn is happening is, if you assume that each ball is selected is replaced before the next one is drawn, means you're just picking up, looking at the color, and you are putting it back if it is not black, okay, before the next one is drawn. So what is the probability that exactly n draws are needed? So certainly I think until you will draw a black ball, that is a problem, that is a success. So drawn black ball, what will be the probability of success? Yes, so total number of balls are m plus n. Out of them, m are black ball. So it's very obvious to see here the probability of success is p equals to m divided by m plus n. The total number of favorable cases divided by total number of exhaustive cases. Okay, now what you are interested in, what is the probability that exactly n draws we needed? Okay, x equals to n means n minus 1 time you are failing, and nth time you will be drawing the black ball. Okay, so it's very simple. What is the failing probability is n, so white ball m plus n to the power n minus 1 time m divided by m plus n. So by following the geometric distribution, that's very simple, pretty straightforward. Now similarly, if you require at least k draws are needed, okay, means you are interested in here in this B case, you are interested is probability that x is greater than equals to k. Okay, at least. Okay, so at least k means you are, at least means x greater than equals to k, and which you can understand by 1 minus probability that x is less than k. And now you know, okay, that is going to be a something like you will, this m by m plus n will come out, and rest of the thing will be a like geometric series with some k minus 1 terms. Okay, and that you know how to sum up the geometric series with some common ratio is known. Okay, all right. So I think I have this here. So x greater than equals to k is at least k is at least k drawn is required to get a probability, means k minus, what does that mean? Means k minus 1 failure. Okay, that also can be understood. So that you can also prove actually. Okay, that's a probability density for that cumulative distribution function for this this geometric random variable. Okay, that also can be seen from here. Okay, so means you can show by following the property of geometric random variable that probability of x less than k is equals to 1 minus p to the power k minus 1. Okay, so if it's less than k means is a discrete one, so less than equals to k minus 1. So 1 minus p to the power k minus 1. That's what, right? Okay, so that you can show by following the geometric series. Okay, so do you have any doubt for this question? I think this is easy to follow. Yeah, it's right. So I think it's very simple, right? Probability of if I write here, so you have this is fx of k, let me do this, is equals to probability at x less than equals to k, and that's equals to summation and I equals to 1 to k, probability that x equals to I, and it's very simple. So probability of x equals to I you can replace here, and then you have this is summation I equals to 1 to k p time 1 minus p to the power I minus 1, that's equals to p time summation I equals to 1 to k 1 minus p to the power I minus 1. Right, so now it's a geometric series, right, with common ratio 1 minus p, so that's equals to, now I can write this, just a second. Yeah, so this implies fx of k is equals to you have this is a p time, you have yeah 1 plus 1 minus p plus 1 minus p square plus and so on plus 1 minus p to the power k minus 1. So this is geometric series like 1 plus r square plus and so on plus r to the power k minus 1. So I think this is very simple, p time 1 minus p to the power k divided by 1 minus p. It's very simple to follow. So this 1 minus 1 plus p is equals to this, and this is equals to 1 minus p to the power k. Okay, so done, right? So this is the cumulative distribution function for geometric random variable. So from here, it is very easy to follow that probability of x greater than equals to k is nothing but 1 minus p to the power. So this is now straightforward. So I don't need to repeat it again, right? Okay. So now the next question is what are the mean and variance of this random variable, this geometric random variable is. Okay. So this can be shown now again by following the approach. Means like you already know what is the sum of this combination of arithmetic series and geometric of x is equals to what? Summation x equals to 1 to infinity x time px of x. Okay, now replace that probability of x equals to x is nothing but p time 1 minus p to the power x minus 1. It's a very straightforward. Now replacing, now p is out, And now you can see, if you write it down, what is this? This is 1 time 1 minus p to the power 0, so 1, plus 2 time 1 minus p, plus 3 time 1 minus p square, plus 4 time 1 minus p cube, and so on. So this is a combination of arithmetic series as well as geometric series. Okay, and how to handle this? If you call this as S, okay, so how to handle this? So this is, you can handle by this. This is your S. You multiply it by 1 minus p, both side, and then subtract. So you will get the, I think this is the way you can find out the S value. Okay, you need to identify this S value. Okay, so you multiply both side by 1 minus p, and then these two things you should subtract. Okay, and if you subtract, p time S is equals to, it will come out as 1 by p, and this will give you S equals to 1 by p square. So now if you replace here, p time S is p 1 by p, so that is what the final answer. Now if you recall, what is variance of x? If you recall, there's going to be expectation of x square minus expectation of x whole square. So it's enough to show, if it is enough to find out the expectation of x square. So again, you have to follow the similar strategy here. Okay, so expectation of x square is what? Summation x equals to 1 to infinity x square time pxx. Okay, so x square time this, and then you will have a, again, in the same approach you can use, and you can find out the sum. Okay, so here is this, and this is going to be, you can show that. I think I have, this is a expectation of x is 1 by x, okay, 1 by p. Now, okay, so similarly, you can identify now expectation of x square, okay. So expectation of x square is equals to summation x equals to 1 to infinity x square time px of x. Now this is equals to summation x equals to 1 to infinity x square time, this px of x is again p time 1 minus p to the power x minus 1. And now this is going to be is equals to, so p is out, okay, and now what you have is, now if I see, this is 1 plus 2 square 1 minus p plus 3 square 1 minus p square plus, right, 4 square 1 minus p cube plus, and so on. Okay, so this you will again call as an S, and again you will follow the similar type of strategy, okay, to find out the final sum. Okay, and you can also then what should be the final answer, you can find out from here. So that's going to be 1 by p square minus 1 by, so this is if you open it up, this is what is this, so 1 by p square and minus 1 by p. So whether it is relating somewhere, so do we have another way to find out? So you can also look at the moment generating function of the geometric random variable, if it is so easy. Okay, so in my opinion, this is expectation of x square minus expectation of x whole square. Okay, so what it will give you, so you have 1 by p square here, so you have okay, so you have to show that expectation of x square, the final answer, I think expectation of x square will be is equals to 2 by p square minus 1 by p. Okay, so that you have to show. So this sum should come out that, okay, final one. Okay, so this final value should come out as 2 divided by p square minus 1 by p. Then your answer is okay. Try it out. Okay, if it will not work, okay, let me know. Okay, I will supply the notes. Okay, in the later case. Okay, right. Now let me. So now we are done. We have covered now almost all important discrete random variables. Okay. Now we are moving forward to define the important continuous random variables. Okay, so among which this uniform random variable is already very much aware to all of you. Okay, it has been identified in the tutorial sheet as well as I think somewhere, I think in the previous lectures as well. Okay, now what you can see is you can by following this so this is a one-dimensional uniform random variable because you have only one random variable. Okay, and why we are calling it as uniform, that you will see geometrically. Okay, now the same definition can be extended to two random the two-dimensional vector, three-dimensional vector, and so on. So I think it is very easy to follow. This is a one-dimensional x. If you have only one random variable, it's a one-dimensional. So if you take the pair x comma y, so x and y two random variables is two-dimensional vector. Okay. Similarly, x comma y comma z is a three-dimensional vector. So three-dimensional random three random variable. If you put in the pair, that is known as three-dimensional, two-dimensional, and so on, multi-dimensional. Okay. So we have talked about jointly. So if you are talking about the, so there jointly means you are working with the pair x comma y. Okay, we have done for the two case, right? Two random variables. Those things can be extended to any number of random, any finitely many number of random variables. Okay, so we will see how this uniform random variable has nice properties when you go with the multi-dimensional one. Okay, try to learn that. Okay, okay. Now it's very simple. So this is fx of x. If it is defined as this, then we say x is a uniformly distributed random variable over the interval is close AB. Okay, and we write x follows this. Now if you draw the picture of this, okay, so what or how does it looks like? It's a line. Okay, okay, so it draws a line. I think this is here. So this is, if you have, this is x, you are taking this x over closed interval AB, and if you're drawing this is the okay, here is you have this y, you can say, and you have this fx of x. What is the curve? Is nothing but this line, y equals to 1 by b minus a. And you can see the distance on any point on this. Okay, so this is a 1 by b minus a. If you look at the distance, everywhere it is uniform. Okay, now this, if you take any interval alpha to beta, okay, which is a subset of closed interval AB, you know how to identify the probability over this interval. Okay, that's going to be integration from alpha to beta fx of x dx. Okay, that's very straightforward. So for alpha beta subset of AB, so this is going to be there. So that's very straightforward. So fx of x is 1 by b minus a. Whenever alpha beta is subset of AB, so fx of x remain constant, that's 1 by b minus a. And this is nothing but the length of this interval alpha to beta, that is nothing but beta minus alpha by b minus a. And it's very certain that when you have a subset, alpha beta is a subset of AB, so length of this interval is always less than equals to length of this interval. So the division will be less than equals to 1. So this will ensure that you have the, this is P actually identifies a probability over it. Okay. Now, if so, let's fix one example. I think I don't know whether it is done in your tutorial sheet or not. So far, I don't know. Okay. Uh, Read it and let me know whether this problem is done. Whether it is in
Yes, no, sir.
one of the tutorial sheet.
No, sir.
Okay, fine. Anyway, we'll try to understand now. So buses arrive at a specified stop at 15 minutes interval starting at 7 a.m. That is, they arrive at, let's say, 7, 7:15, then 7:30, and so on at 15 minutes interval. Okay. Okay. Now, if a passenger arrives at the shop at a time that is uniformly distributed between 7 and 7:30. So during that interval, so 7 to 7:30, that's a 30 minutes interval. That's a uniformly distributed. Find the probability that he waits. Okay. So he waits less than 5 minutes for a bus. Or he waits at least 12 minutes for a bus. So now if I define x as the time in minutes past 7 a.m. so after 7 a.m. in minutes that the passenger arrives at the shop. Okay, after 7 he arrives at the shop. What the time in minutes till 7 till 30. Okay, 7 to 7:30 we have to only measure. So then x will follows the uniform distribution over the interval 0 to 30. Now, if you look at the first problem, he should wait less than 5 minutes for a bus. So what is the interval time he should arrive? Is less than 5 minutes. So after 7, next bus is what? 7:15. So he should arrive between 10 to 15. So, right? So he should arrive between 10 to 15, 7:10 to 7:15. Then he will wait at less than 5 minutes. Or he should arrive between 7:25 to 7:30. Less than, strictly less than. Okay. Then, so these are the two events, okay, where it will fall. Okay. And both are mutually exclusive. Okay. So this is going to be equals to probability that, so it's equals to probability that you have 10 less than x less than 15 plus probability that 25 less than x less than 30. And this is equals to, so now just now we have seen that's 15 minus 10 divided by 30 plus 30 minus 25 divided by 30. Beta minus alpha if I refer that exercise just now we have done. Okay, so this is going to be, so it's going to be 5 by 30 plus 5 by 30, so it's going to be 10 by 30 and it's going to be 1 by 3. Yes. Now, if you look at this, at least 12 minutes for a bus, he should wait at least 12 minutes for a bus. So when he should arrive? So only two buses are there at 7:15 and 7:30. So when he should arrive is between 7 to 7:03 and 7:15 to 7:18. Right? These are the only two possibilities where if he arrives, he should wait at least 12 minutes for a bus. Okay? And you do again in the similar fashion. Okay? Then you can find the final answer. So 7 to 7:03 and 7:15 to 7:18. So you have 0 to 3x and 15 to 18x and you have the final answer. Okay? Right? Now, that's another exercise. This is an exercise. I think this also can be done easily. Okay, so I don't think so I have to explain this. So you can do, okay, you have a 2 minutes time, you can verify the following. Okay, So x follows the uniform distribution, then mean is nothing but the mean of this AB, a plus b by 2, and variance of x is b minus a whole square by 12. Okay, so you do verify. So expectation of x mean is already has been calculated. For the variance of x, you need to identify expectation of x square. Okay, try it out. Okay, try it out just now. So you have to just replace here x square. That's it. So what is the expectation of x square is, I think this is here is x square, so x cube by 3. So you have 1 upon b minus a times 3. X cube is so b cube minus a cube. So that's going to be, now you know how to b minus a into a square plus b square plus ab, right? A square plus b square plus ab divided by 3, right? And now you subtract with the this whole square, and then you verify that variance of x is b minus a whole square by 12. Okay, so that you can do later on. Okay, right. Now,
Sir, I
yes,
don't understand.
yeah.
Sir, I don't understand the last step you done, that b cube minus a cube upon 3 upon b minus a. I don't understand.
No, what is x square integration? If you don't, I don't know, means whether you have pick up the pen and paper or not. I don't know, means like, see, I have asked you to solve out, right? If you only follow here, it will be very
Okay,
difficult.
okay. I get it. I get it.
Okay, so x square integration is x cube by 3. So upper limit minus lower limit. Okay, it's a very simple exercise.
Okay.
Now, this next example is as follows. The current in a semiconductor diode is often measured by the Shockley equation. So the following is the Shockley equation, okay, which I don't want to worry about to define it. Okay, so where this individual and the notations are defined as follows. So V is denotes the voltage across the diode, I naught is the reverse current, A is a constant, and I is the resulting diode current. So you are in the ICT, so you may very well understand this, all the things. Okay. Now, what is additional? This is Shockley equation. So what is additionally given to you is that if you have to find expectation of I. So you have been given with A value, I naught value, and you have been given that V follows the uniform distribution over the interval 1 to 3. Okay, so I naught is constant, A is constant, but it's a function of V. Okay, so V is a random variable, so this complete will identify a random variable. Okay, so this expectation of I is nothing but expectation of this. Okay, and you have to fix all the things. So I is nothing but G of V, and with where I naught value you can put 10 to the power minus 6. A value is 5. Okay, so expectation of y is equals to integration minus infinity to infinity G of V, Fv of V. So now Fv of V is what? 1 upon 3 minus 1. and it is only non-zero between the interval 1 to 3. So what will be the final here is integration 1 to 3. Okay, so 10 to the power minus 6 times e to the power 5 v minus 1 divided by 3 minus 1, that is 2 dv. And now you know how to integrate this e to the power 5v, and you put upper limit minus lower limit. Okay, so that will give you the final answer here. Okay, right. Okay, so you can also verify that the final answer is 0.3269. Now,
Why are we not multiplying by V to find the expectations?
where?
Can you go through previous slide here? Like, why are we not multiplying by V? The original
See,
function is
if you recall the previous lectures, what is the expectation of g of x if x is a random variable? Is going to be, for the continuous case, is integration minus infinity to infinity g of x time fx of x dx.
then what is FV here? F of x here.
Huh?
What is f of x here in this case?
fx is a PDF for x random variable. So here is FV is a PDF for V random variable. And did you miss the class? I don't know. We have done
Yes,
it
sir.
long back.
Yes, sir, I got it.
Means all the recordings are available. I think you can go and revise all the things. These things will be used in rich when you talk about this statistics and all later on.
Yes, sir, I know about that, but I recently written the expectation formula with V into that function, so that's why I got confused.
Okay.
Like here, we are not multiplying by V.
Yeah. Okay. Yeah. Okay. Fine. Let's move forward now. Okay. Now we want to extend this uniform random variable. This was a one-dimensional random variable, which was only related with the over the interval. You have this is, if you recall, this closed interval AB. So what will be the extension of this on the two-dimensional case? So in the two-dimensional case, that you have a certain region. Okay, if you talk about the continuous case, because this is a continuous case only. Okay, x is a continuous random variable. Here, uniform random variable is continuous. Okay, so you have a region which is covered by this xy plane. So x is a one random variable, y is another random variable. So, and now you can draw this. This is a region. So this is a part of the region. R1 is a part of region. This R. So if you recall the double integral, okay, if you recall the double integral from your calculus part, this double integral dA, okay, over R will define the area over the region. Okay, so this is nothing but the area of R. Right? If you look at back in the vector calculus or multiple integral calculus, okay, so that is actually identifies the area of the region R. So earlier we were having on the one dimension, so on the x you are only dividing the, means you have the length of the interval. Now can you relate now? Okay, what will be the what will be the possible generalization of this over uniform random for two-dimensional one case?
In the integral which you have mentioned in black color, it would be over the region R1, right? Then we would divide it by the area.
This is a 1. This is 1. This is equals to 1.
Okay, okay.
Now can you give me over the two-dimensional what will be the my possible way of defining the uniform random variable? Yeah. Yes, what will be the possible extension or natural extension you can say?
1 over x2
Hmm?
1 over x 1 over x2 minus x1 multiplied by y2 minus y1. The limits where the region limits.
No, you are talking about a uh, only rectangular region.
Sir, it will be the integral.
So you are
of
x2
this.
minus x1 into y2 minus y1. What will be that? That's the area of that rectangle x1 cross x1 to y1 and cross x2 comma y2.
Sir, will it be the integral of the CDF? CDF in terms of the two random variables over the region, which we are considering.
This one?
So integral
This
of
one
the
you are telling?
CDF over the.
CDF. But
Yes.
what is CDF? I am trying to identify the PDF. I am trying to identify the PDF, probability density function. So that uniformity will be mentioned. Okay, what do you understood by uniformity? Here, so 1 upon the length of the interval.
For each
1
value,
over the area of interval.
Yeah.
Yes, sir.
So you have given, the one person has spoken and he rightly mentioned 1 upon x2 minus x1 into y2 minus y1. Why? Because that if it was correct, if it is, you are considering only a rectangular region, okay? If you have the rectangular region, x1 to y1, and you have some x2 to y2. This is the rectangular region. So if you're talking about that, wait a minute, x1 to here is x2 and y1 to y2. Yeah. So if you recall that, that's what was he said is x2 minus x1 into y2 minus y1, because it's a very simple geometry to handle. So that's why people looks into this first. Then they will try to generalize to any regularized region. So this x2 minus x1 is nothing but the length and breadth of this rectangle, and what is that? This product is nothing but the area of that region. So, but everywhere the shape cannot be a rectangular region, it could be any region. So it is perfect to identify the two-dimensional one is 1 upon area of R. And if we do agree with this, what is the possible extension of this in the three-dimensional case?
Then it will be volume of that region.
Yeah. So because if you go and check that how if you check that in your integral calculus, okay, there if you try to talk about the area of the region, how it has been approximated by using the rectangular region, right? Subdividing by you have horizontal line and vertical lines, and you are creating a rectangle meshes, and you are just using that Riemann integral and all those stuff, and then you are approximating, then putting the summation, and that in the limiting case it is converging to the double integral R. And when you talk about the volume, means like in the 3-dimensional, you will talk the volume, then it will, instead of a rectangle, you have a cuboid, right? Cube, you can say. Okay, and so on. Okay, so it is perfect to identify the 2-dimension is 1 upon area of R. So what is the probability of any part of this R1 now? Means R is the full region, R1 is a part of R. So what can I say about the probability of this R1? Can I say from something here straightforward? What is the probability of R1?
Sir, I think it will be area of R1 divided by area of R.
And that is certainly less than equals to 1, because area of R1 is certainly less than equals to area of R. Okay. So this is in the same line, okay, which we just now followed for the uniform random variable over the interval, now over the region, now over the volume, and so on. Region means the 2-dimensional, and you have over the region means 3-dimensional if you talk about volume and so on. So here it is the definition, the random vector. So as I told you, when you make a pair of 2 random variables, it is named as random vector. Is said to have a uniform distribution over the 2D region R if its joint PDF is given by this. So it's now perfect to say this. Okay, and same thing can be extended to 3-dimensional, 4-dimensional, and so on. Okay, right. And in the above case, you have A is any part of the region R, and you have this is going to be area of A divided by area of R, because fx of y, this PDF, if you put down here, what is that? It's nothing but 1 upon area of R, that is out, constant. Okay, and double integral A dx dy may denote the area of the region. So this is also fine. Okay, right. Now here we try to understand when you have the rectangular region. Okay, what is the nice property with it? So suppose that x comma y is uniformly distributed, this vector, over the following rectangle R. Then x comma y are this x and y, these x and y are independent random variables. So if they are uniformly distributed over the rectangular region, then they are nothing but independent random variables. And that's a nice property. So how would you verify that these are independent random variables? If their joint PDF can be written as, can I write it as fx of x into fy of y? Yeah, can I do this?
Yes, sir, in this case.
In this case, yes, it is very straightforward, right? Because 1 upon a and into 1 upon b, obviously we are talking about a and b are non-zero. We are not talking about a point, we are talking about a rectangle. So a and b are non-zero, we are using, and 1 upon a and into 1 upon b. So 1 upon a, x will follow the uniform distribution over the interval 0 to a. So its marginal or its PDF is nothing but the fx of x is equals to 1 by a whenever x lies between here and 0 otherwise. Similarly for y, fy of y is 1 upon b whenever y lies here and 0 otherwise. Okay, and certainly 1 upon ab, you can write 1 upon a into 1 upon b. Okay, right? And whenever xy will fall into this region, if you try to draw this region, okay, this is the region. Okay, you draw, you take any point, so it's going to be 1 upon AB, that area of the rectangle only. Okay, and it's non-zero, neither x is 0 nor y is 0, so 1 upon AB. Whenever here, okay, and here, whenever you have otherwise, okay, whenever it is outside of this rectangle, it is a 0, okay, because of the property. So it can certainly be written as the product of these two, and you can certainly say x, y are independent random variables. You
Sir,
can
here
also check.
sorry, sir. Sorry to interrupt, sir. Sir, I just had a question that here are we assuming that x is a uniform random variable and y is a uniform random variable?
Yes, we are assuming that they are jointly uniformly distributed. Okay, and we are also assuming that x and y are uniformly random variable. We are assuming those two things.
Okay, sir.
Okay.
Yes, sir.
Right. So you can also do by using the CDF, joint CDF, this way. Okay. Okay. So this is going to be, and I think it is come out. See, one thing, if you try to identify from here, and if you try to identify fx of x from here to here, marginal CDF, okay, it is going to be come out as x by a. Okay, and which is nothing but the CDF of uniform randomized. So it is not necessary to assume that. So it is assumed that xy is uniformly distributed over the following rectangular region R, then they automatically will come out as uniform random variables. Okay, so it's not required to assume.
If two uniformly distributed random variables have a distribution which is not rectangular, then they would be dependent, or they won't be independent. Can we say that?
That I can't guarantee. Okay, it may be or it may not be. I don't know.
Okay.
Okay. So here is, okay, you can try this exercise out. Okay, probability that x less than equals to x, y less than equals to y, and you know what that is going to be 1 upon AB is out, and you have the integration from 0 to x and 0 to y dy dx, and if you integrate this, it's going to be x times y by AB. Can you work out this? If you have any doubt to reach this x times y by AB, you please raise your hand, which will tell me. Yeah, it's very straightforward, right? Now, can you also verify that this fx of x, it's written, all the steps are written here. Can you verify all the steps are correct here? That marginal density, marginal CDF.
Yes, sir.
So similarly, you can also verify that this fy of y is equals to y upon b. So you have from here above and here discussion, you have this is fxy of x comma y is equals to fx of x into fy of y. So this also identifies that both x and y are independent. And you know, for the continuous random variable, you know, fx derivative will define the small f, okay, PDF. So 1 by a. So this is true for x 0 less than equals to x less than equals to a. Okay, and 0 otherwise. So you are working here, this here, everything is work out here is 0 less than equals to x less than equals to a, and 0 less than equals to y less than equals to b. So keep in that mind. So when you differentiate, you have the fx derivative is 1 by a over the interval 0 to a, otherwise 0. Similarly, for fy dash is 1 by b, 0 to b whenever y lies between here. So so that PDF is nothing but the PDF for the uniform random variables over the interval 0 to a and 0 to b respectively. So that will automatically come out if you take the two-dimensional uniform distributed random variable over the region, rectangular region, it will be automatically come out that they are individually, they are uniformly distributed, and they are independent. Okay, right, fine. Now it's a very important random variable which you will see when you go for some advanced topics. Okay, and this is actually given by De Morby. Okay, when he was doing some experiment with respect to the binomial random variable, and what he found is when n is going large, and if he's plotting, means if he's keep on performing the Bernoulli trials, okay, and if you try to fit the curve through the given through the output, okay, what are the points he is noting down, it is going to be smoother and it is going to be bell shaped curve. Okay, I have that picture, I will also show you. Okay, and later on you will see at the end also center limit theorem will tell you, okay, that if you go for n large, okay, any type of random variable, they will actually converge to that, the curve will converge to the normal random variable. Okay, so it is very important with respect to the research perspective. Okay, let us see further, I mean it's like what we can do more about it. Okay? Right, so let's first let me give you the definition. Okay, then we will see that plot. Okay, right, so a random variable x is said to be normally distributed with following parameters. Okay, one parameter is mu and another parameter is sigma square. Okay, so these are essentially nothing but they are turned out to be as mean and variance respectively for this random variable. And we write x follows normal distribution n with mu comma, so these two parameters has been mentioned here, if its PDF is following. Now if mu equals to 0 and sigma equals to 1, it is easy to take. Okay, so if you have this, let's say mu equals to 0 and sigma equals to 1, then you have fx of x is equals to 1 upon square root of 2 pi and e to the power minus x square by 2. And I think you are very much familiar with this function, where it is appearing. Can you tell? This function, did you see anywhere?
So in the Gaussian distribution of the velocities of a ideal
Gaussian
jet.
distribution.
Yes.
Okay. Anywhere else? Have you ever worked out with error function? Okay, if you integrate this, suppose, so what is the challenge now? Okay, let's see. So 1 upon root 2 pi is coming out because to satisfy the normality condition. Okay, because it's going to be a PDF for a normal random variable with mean is 0 and variance is 1. Okay, so this 1 by root 2 pi is a weighting factor. And now if you integrate this e to the power minus x square by 2, the analytical expression is not possible. Okay, this integration cannot be solved analytically. So certainly you require approximation. So here you have to take the approximation like trapezoidal rule, Simpson's rule, and so on will come into the picture. Okay, those you have learned during your, I think, numerical course. Okay, so this is a challenge here, e to the power minus x square by 2. This is the expression. Okay, and whenever either x goes to infinity or x goes to minus infinity, this tends to 0. Okay, so it is a well-defined function, so there's no problem in that. Okay, right. Okay, so here is the plot, what the de Morvis observed. You can see he has performed the 10 random experiment, and he has plotted the chance that how many success he has got. Okay, right? So this is I think 0 to 10. 10 times he tossed the coin. Okay, so this I think mass function of a binomial random variable, because okay, as n becomes larger than n. So probability of success here is fixed 0.7. So p is fixed 0.7. Okay, now so the means like this is the curve, which is this is the curve which is passing through this points. Point 0.7 is the probability of success, right? So if you recall the binomial random variable, what is the probability mass function? So x equals to I is equals to, okay, probability of x equals to I is equals to NCI, okay, p to the power I time 1 minus p to the power n minus I, right? It was there. So p is 0.7, okay, and 1 minus p is right 0.3. Okay, so here is, see, when so here's plot for NC0, NC1, NC2, NC3, NC4, and so on. These all these things are probability mass function is plotted here when you take n equals to 10. So when he is take n equals to 20, he has plotted all the data. Okay, and for n equals to 30, he is the for different values of n equals to 10, n equals to 20, n equals to 30, and n equals to 50. He has plotted the probability mass function, the values, approximate values. Now you can see as the n increases, they are going much dense. Okay, much closer, right? Here, many of them are lies here, right? When you have 50. And if you try to fit the curve here, previously it is coming like here, but afterwards it's like, and then it is going down. Similarly here. Okay, so if you increase more n, it will be more smooth. Okay, and if you go back and plot, I think you are comfortable in MATLAB, and you can plot this e to the power minus x square by 2. Okay, very easily. Okay, and you can see that is going to be a bell-shaped curve, and it's going to be symmetric about the 0, x equals to 0. And if you work out with x equals to mu, so if you look at here, okay, so x equals to mu. So what is happening at x equals to mu here? So this is 1. And you can see that maximum height, what it will be maximum height is 1 upon square root of 2 pi sigma, which will be occurring at x equals to mu. That you can also prove. Okay, that will have a maximum at x equals to mu. Okay, and this is going to be symmetric about the line x equals to mu. So if you put mu equals to 0, you are symmetric about the line y-axis. Okay, right. We will talk more about this more detail. Okay, right. Now, so let's try to first verify that mean of this normal random variable is mu and variance is sigma square, and fx of x is here. So here what I will try to show is, what you can show is expectation of x minus mu is 0. If I show this, this implies expectation of x equals to mu. Okay, I will try to show this expectation of x minus mu is 0, and because expectation is linear, I can use that fact and I can prove that expectation of x is mu. So why I have chosen this x minus mu here is because of this x minus mu is sitting in the argument. Okay, so because we have to deal with the integral, okay, which is very complicated. Okay, so if you if you write down expectation of x minus mu, what is that? X minus mu time fx of x. So what is fx of x is 1 upon root 2 pi sigma time exponential of minus 1 by 2 x minus mu by sigma whole square dx. Now you know how to solve this type of integral is we have to use the substitution method. So what is the first substitution we will make is x minus mu by sigma we will substitute by y. Okay, and then try to see what will be the change. Okay, now first thing is upper limit and lower limit. So whenever x is minus infinity, y is minus infinity, and x is plus infinity, y is plus infinity, right? It will not change anything because x by sigma minus mu by sigma, and negative of some minus infinity is again, if you are adding something else, again minus infinity, and by mu by sigma will not make much difference to infinity. Infinity minus mu by sigma is infinity. Okay, now dy, so dx also should be replaced from here. Dx is sigma time dy. Okay, or dy is dx by sigma. So this sigma can be taken here, dx by sigma, and can be replaced by dy. Now x minus mu by sigma is y. Okay, so this is e to the power minus y square by 2. Now x minus mu, what is x minus mu from here? Sigma y. So this is a sigma y. And this sigma is already adjusted here. Dx by sigma is dy 1 upon root 2 pi. Okay, now sigma is coming out, sigma by square root of 2 pi, integration minus infinity to infinity, y time e to the power minus y square by 2 dy. Now see, y square by 2 derivative is y dy. Okay, now this integral is easy to solve. Okay, so if this integral, so substitute y square by 2 is z. So from here y dy is dz. Okay, and you can now, this integral is transformed into what? You have this is sigma square root of 2 pi time integration. So y square by 2 is z. So how will you change the limit? So what we can do is here is, so this is a, okay, this is a derivative, right? We know. Okay. So you have this is you have this is you can what you can do is here is a improper integral, right? So you break it down minus infinity to 0 and 0 to infinity. Okay, so you break it down minus infinity to 0 plus 0 to infinity. Okay, otherwise it will not be possible. First thing. Okay, now this is a e to the power minus y square by 2. So now you can use that fact, improper integral. Okay, you are aware about this, right? So if I okay, I will write some few steps. So sigma by square root of 2 pi limit t tends to minus infinity integration. You have let's take, instead of t tends to minus infinity, so t to 0, you have e to the power minus wait a minute, we have, this is going to be what is that is you have y time e to the power minus y square by 2 dy plus limit sum, you have, this is x tends to infinity integration 0 to x y time e to the power minus y square by 2 dy. Okay, now you apply this this improper integral property. So sigma by root 2 pi limit t tends to minus infinity, and you know this is antiderivative of this is nothing but e to the power minus y square by 2, right? This integration and t to 0 plus limit x tends to infinity, and you have, this is going to be, you have e to the power minus y square by 2 0 to x, and now you this sigma by square root of 2 pi. Now this is going to be limit t tends to minus infinity 1 minus e to the power minus t square by 2 plus limit x tends to infinity e to the power minus x square by 2 minus 1. And now if you apply the limit t tends to minus infinity e to the power minus t square by 2 tends to 0, limit x tends to infinity e to the power minus x square by 2 is also 0, 1 minus 1 is 0, so it's going to be turned out to be 0. Okay, right? So this is what about the mean. Okay, for the variance, okay, so for the variance here you can use the fact, so variance of x, what is the definition? Expectation of x minus mu whole square, okay, is equals to sigma square. So you use this fact because of x minus mu is sitting inside, so you know okay, then you can handle this. Okay, right? So here is this, I'm just giving you some the important point here is expectation of x minus mu whole square. So 1 upon square root of 2 pi sigmas time this is a x minus mu whole square time fx of x. Okay, so 1 by root 2 pi sigma is out. Now again you will use the same substitution, x minus mu by sigma is y. So this x minus mu whole square is nothing but sigma time y whole square. Okay, and dx by sigma will be dy. So sigma square is here and y square is here. Okay, now to establish that this is equals to sigma square, what you have to do is you have to use here product rule for integration of y square time y to the e to the power minus y square by 2 dy. It is not easy to do directly, okay, because y square is sitting here. So you take y time y into e to the power minus y square by 2 because you know you can integrate this. Okay, so when you do so, so this is going to be, can be written as follows, and then you can, and also you can use this fact 1 upon square root of 2 pi integration minus infinity to infinity e to the power minus x square by 2 dx is 1. Okay, so use the product rule to establish the final answer is sigma square. Okay, so the proof will be in the same line. Okay, so try to do that. Okay, if it is not done, let me know. I will again I will supply the notes then in that case. Okay, right. I think we can close now. If you have any question, you can ask. Okay, thank you.